Start. So luckily we have the figure from yesterday still on the board. So we're talking about statistical decision theory, basically formulation of the setting where there is a lot of stuff you don't know. You get to see some of it, you get to see an observation, you want to take an action, and the cost that you pay depends on what the unknowns are. Okay? This is done on the Rumsfeld quote about the known unknowns and the unknowns unknowns. All that? Okay. Anyway, when you start a war, I guess there's all these unknowns, and the outcome of the war is obviously dependent on a lot of unknowns. So we gave these some random variable names. The unknown world is a state, which is a random variable called omega. The observation is x. And the action is, I'll leave this open for now because I want to give it a slightly different name now. Okay. So, and what did we assume we know? We assume that someone gives us a cost function or let's call it a cost function or risk function or loss function. Anyway, something that we want to be low. For what happens if we take a given action alpha, given that the world state will be made. Okay, so that's these are the costs that we know, and we also assume, which is a pretty wise assumption, but we make it for now, that we know that the probability distribution of observations given world state, and we further assume that we know the probability of the prior probability of a world state. Okay. So if the world state is whether it will rain or not today, so P of omega says what's the prior probability of that happening. And from that we concluded that we actually also know the joint distribution because this simply holds, right? And I started saying that there's a whole community, the non-Bayesian community, that's opposed in certain settings to assuming that you know this prior over world state, or know it, or that you should take it into account. And we'll give several examples with that's actually a sensible argument. Okay, but for now, we basically assume we have a full probabilistic model where all variables of interest are random variables, and we know how they're distributed. Okay. But still there's a question, even if you know all these things, what's the best way to behave, right? So the key question that we have here is what action should we take after observing X. Okay? Okay, so basically what we're looking for is what sometimes called a decision rule. So it's a function from what to what? From observation to actions, right? So let's define that. So we say decision rule delta is a function from observations x to actions a. So roughly speaking, delta we would say it's from x to a. And as I said, x I use interchangeably for the variable itself and for its domain or for its possible variables. Okay, so delta. A decision rule is a function, okay? And that tells you what to do in any given situation, right? So if you see, let's say x is something like stormy, sunny, cloudy. So the decision rule will tell you in each situation what's the action to take. Okay, so one decision rule might tell you that if it's stormy, you should take a jacket and Another decision rule might say that if it's stormy, you should stay at home. Okay. Okay, and we're looking for such a rule, and we'd like to find a good rule. Okay, so what does it mean to find a good rule? So we started hinting at something that might be reasonable yesterday. We said if these are the costs you pay, okay, these lambdas, then it makes sense to minimize what? Well, but the cost is a random variable, right? It changes. So, right. So expectation. If you have a random variable and you want to say minimize that random variable, since it's random, you can't really minimize it in all cases, right? But you can talk about its expectation, which is a single number, and you might want to minimize that number. Okay. Okay. So let's make that a bit more formal. So let's say, given a strategy that, sorry, I call it the decision rule, sometimes called the strategy, delta, the random RV is random variable. We have a random variable that's the following random variable, lambda of delta x given omega. So what is that? What's this random variable?
Cost. Action?
No, that's the cost, okay, that I pay when taking decision rule delta, right? Okay. Why is it a random variable? Because let's say I wake up in the morning, I see this observation x, okay, so I see that it's stormy, okay. In the background, there is the unknown real outcome of the day, which is whether the day will be rainy or not, right? So there is this thing omega, right? By the end of the day, I will know it, but it already exists there anyway, okay? This thing. So these two things are random variables in the world, right? What I observe and all the stuff that I don't know, okay? So given what I observe, my decision rule tells me what to do, right? So there's delta x, which is what? An action, right? Okay? And now there's the cost for that action given that state of the world, right? So every time I wake up in the morning, these two things are random variables that are there, and this thing is also a random variable, right? It's the cost that I will pay for taking the action that my rule tells me to, given the world state, right? So when will I get to see this number? When the day is done, right? So when the day is done, I will get to see this omega. I will also suffer its consequences in the form of this number. Yes?
Lambda is a function from what to what?
Here it's a function from both an action and the world state to the real numbers. Okay? So this would be from actions and world states to the real. Okay? So it's essentially if you have a finite number of actions in the world state, it's just a table of numbers. Okay?
Are we treating here omega as a random variable that has its own probability distribution, or as a single instantiation?
Here?
Yes.
Here it's a random variable. Okay? So all this thing is it's a random variable depending on two random variables. Okay?
Conditioned on.
No, so it's not. No, so this. Okay, this is the notation that you didn't like yesterday. I guess you're highlighting why you didn't like it. But this is just a function. So lambda is a function of these two variables, and the way you calculate this function is you go to that table there, and you look up its value.
So treating it as a table.
Yeah. Okay. So.
Gamma not doesn't include probability.
Sorry.
Delta.
Delta. What about it?
No, the lambda.
Yes.
Doesn't include probabilities.
No, it's just a table of numbers. Okay, so if you have
Cost for something.
yeah, so let's say you have what do we have here? Actions and world state. Okay, so these are just numbers. Can even be negative. Doesn't matter. Okay. So if omega has a value 2 and the action is 1, then...
So why you call it random variable? It's deterministic.
Which one?
The
No, because lambda, the table itself is deterministic, okay? But the entry, the point that you look at in the table is determined by both x and omega, right? So you wake up in the morning, you see observation stormy, okay? Your decision rule tells you to wear a jacket, okay? So that points you to a particular action here, right? Then in the evening you see what omega was, okay? That's also random, right? So let's say it points here, then lambda is this one, okay? On a different day you might wake up, you might see the same observation and take the same action, but then in the evening you actually see that this is the word state, okay? So now lambda is this, right? It doesn't have the same value, okay? It's a random thing.
I would say only the omega is right.
No, but lambda,
Is
okay, this
true.
thing, okay, let's call it, all this thing is a function g of x and omega, right?
Yeah, a function of a random variable is also random.
Yeah, okay? So this thing, all this thing, if I give you the random variable x and the random variable omega, okay, you can calculate this number, right? So it's a function, g, let's call it g, of these two things, okay?
I think maybe one
Yeah.
is confusing this when omega is given, alright? Given omega, then it's not omega.
Yeah, okay, so that's the notation that we mentioned yesterday.
No, but
It's
given
just a
omega is
notation.
still a random vector.
Sorry?
Random variable.
Still a random variable, also given omega.
No, but given is a, okay. Let's. I'm willing to do this for from now on if it simplifies things. Okay, so let's do it. Given that there's enough opposition in class, let's just do it this way. Okay. So is that better?
We might want to actually condition on omega.
Yeah. Yeah. Okay. All right. So see, there's flexibility here. Okay, so from now on, we denote the cost of action and world state by just lambda alpha comma omega. Okay? So, okay. It used to not be confusing, but it might have actually been confusing because no one said anything. Okay, so is this clear this way? Okay, so basically, given variables x and omega, there's a new random variable, there's a function of those, which is the price that you pay for taking the decision rule delta on x, and then paying the cost that you pay. Alright? So for every value of x and omega, there's this price that you pay. Okay? Yep.
Delta gives the same result for every x?
No.
I mean, it
Does
gives
it
different
always-
results for...
I think what you mean to ask
Yeah.
is whether it always gives the same result
Yeah.
for the same x. So in other words, is it deterministic? So we assume it's deterministic, and you might have an exercise where you show that if you made it non-deterministic, it wouldn't help you. Okay? Sort of makes sense, right? Because if there's the right thing to do, there's probably no reason to do a different thing. Okay? Sometimes when you're playing against an adversary, it makes sense to randomize, as in game theory, but in this context, it doesn't. Okay? And I also said it's a function from x to action, so it means that for every x, there's a particular action that you take, and you always take that action. Okay? But it's a good question. So this delta of x is a function. So given x, delta x is uniquely determined. It's just the action that you take at taking that observation. Okay. So there is this random variable, which this is how it's defined. We might want to call it. We can denote it this way as well. Anyway, it's a random variable. It's what you suffer for playing your decision. Okay. All right. So now, what does it make sense to do with this random variable?
By the probability of omega given each.
Okay, you're already giving the answer to you're one step ahead because you're suggesting a particular strategy, right? But we don't know in what sense that strategy is good. Okay, so this is the thing that every day this is the cost that you pay every day. This is the amount of shekels that you put in the penalty box at the end of the day after seeing what actually happened. And it's a random variable, right? Every day you wake up, you see a particular x, there's this omega in the background, you don't know it,
you play what you play, it's delta x, and you put the money in the box, right? So this thing is random. So intuitively, we want to pay as little as possible, right? But since we pay a different amount every day, it's a random thing, it might make sense to minimize the expected value that we pay, right? The expected cost. Okay? So let's see what that means. Let's say it makes sense to look for delta that minimizes the expected cost. Okay? So let's make that more formal. So what's the expected cost for a particular, so now the game is that you give me a particular delta. I want to evaluate how good that delta is. So I calculate for that delta, what is the expected cost, okay? So I want to find the number that tells me if I were to play this delta again and again, okay, over time, what would be the money that I have to put in the box, okay? So what is this thing? Well, actually, I should have written delta here as well, right? G is dependent on that. Okay. So the expected cost is, I'll use this notation, so it's the expected value of lambda delta x and right? So this is the expectation. Is that, sorry, yeah.
I didn't really understand why it makes sense to look for. Isn't like delta certain, for example, with the example of the rain, isn't that like how don't want to minimize the expectations for the value you get over a year of when you sum up delta, and not you don't want to look for a delta that minimizes.
But
given a delta, you want to minimize the value. You make a decision that minimizes the value you'll get from a certain delta.
yeah, so I'm looking for a particular delta. I'm now going to search supposedly over all possible decision rules. Okay, each decision rule will have its own expected cost. So if I were to play that rule again and again over time, what is the expected cost that I have?
Oh, so you want to minimize you want to find a rule which minimizes.
Yes, yes.
Oh.
Shall I say that? Look for delta. Okay? Okay, so what is this expected cost? Here is the cost, right? That's the random variable. I want to talk about its expected value. Okay, so this is the expectation operator. Is that familiar to everyone? Okay, so I put a random variable inside, and this thing is usually called, is denoted by R of delta. And I use square brackets here because what's the input? What is delta? As a function, right? So I have a function that takes a function and returns, what is this thing? A scalar, right? The number. So something that takes a function and returns a number is called a functional, and it's usually denoted by square brackets, okay? So R of delta is a functional that returns the expected cost for this delta, and it's known as the expected, known as the overall risk. It has multiple names in different communities and books, etc., but it might be called the expected risk or the overall risk. Called the overall risk because it's overall, like when taking expected value. Okay, so that's the expression. There's a simpler way of writing it. So basically, we need to sum over all random elements here. So what is random here? What are the random things here? The world state and the observation, right? Okay. So we calculate this by summing over all random things, taking their probability, which we know, and multiplying by the value, so lambda of delta x and omega. Okay? Does this make sense? It's actually called the rule of the, or the law of the unconscious statistician. This thing that we just did. Okay, let me state the law. Oh, yeah, it's actually, sort of a lemma. It says that it's the expected value of f of x. So let's say x is a random variable and f of x is a function of that variable. So f of x itself is a random variable. Okay, let's denote by z. Okay. So in order to do this thing, one sort of the textbooky way of doing it is to look at this variable z. Okay, figure out how it's distributed. Okay, figure out what its distribution is, and then do sum over z p. Right, this is the definition of expected value of a random variable. Okay, but you can easily convince yourself that this is actually equal to sum over f of x here, which is what we did here. So I guess this is sufficiently intuitive for you that you wouldn't even think of doing this, but just so you know, you're using it.
Actually, we measure the expectancy for each x separately.
No, why did you say that?
They don't influence each other.
You mean here?
No. If you have observation A and take a decision, and you have the decision just minimize the expectancy for observation A, you have the observation B.
Okay.
Alpha 2. And the action that minimize the expectancy for alpha 2, and alpha 1 don't influence alpha 2.
So I think you're referring to how this can be minimized?
Yeah.
Okay, you're right, and I'll show it, okay? Okay, so this is just to say, you have this function, you have the expected value of this supposedly complex random variable, but the way you do these things is just you look at the random variables inside, and you take the expected value, you use the distribution over these variables to take the expected value, okay? So this is just an instance of what I had there, right? Is that okay? Okay. All right, so this is the definition of the overall risk, and given a particular delta, you can go and calculate this thing, right? Because you know all the components here. You know P of x and omega for every value of x and omega. You know these things, lambda out. So delta x is a particular action for a particular decision rule. So you can, if you have these numbers, you can calculate it. Good, okay? All right. So, so we will say that the optimal Bayesian decision rule is the one minimizing R of delta. Okay, so this is a statement. I mean, I'm not telling you that this is the best thing in the world. I mean, axiomatically, you have to behave this way. This is one statement of optimality, one criterion of optimality. There might be different criteria, and they might have their own justification. This is something that sort of makes sense, right? Okay, it's not globally or religiously true, but it's a criterion that makes sense if what you want to minimize is your long-term cost. Yep.
In that case, we assume that we know P of x and P of omega for all x and omega.
Even worse than that, you assume P of x, P of x and omega, the joint distribution, okay? Which I assume you know these two components, so you know that as well, okay?
If you assume they're independent.
No. This is always true. It doesn't talk about independence.
I mean, it's not enough to know P of x and P of omega.
No, but this is P of x conditioned on omega and P of omega, okay? And this is always true, okay? It's important, okay? All right. I could have just said I know this thing, okay? But I wanted to say that I know these two things because later on I will want to say that I don't know this, Okay? I could have said I know this to begin with, because that's what I used to.
This is the simplest, like, optimality criterion that we're using.
I would say, I mean, that's why we teach it now. I mean, given this framework, it sort of suggests itself, right? And it is pretty natural. And mathematically, I would say it's probably simple. Okay. So, all right. So, what is this thing? This delta, the delta that minimizes this thing. So, yeah.
Can I go back to the
Sure.
X is what you know, right?
Yes.
So wouldn't you like to know P of omega when you know X? When you know that X is there?
I would very much like to know it, and I can calculate it from here, right? You will see that this is in the solution. This
So
is
we
the
can
thing.
calculate it.
Yeah, this is Bayes rule, right? We talked about it yesterday. So P of omega given x is just P of, well, there are different ways of writing it. P of x omega divided by P of x, which is equal to P of x given omega times P of omega, or P of x, right? This is station.
So you need to know P of X.
Yeah, but P of x is also something that I mentioned yesterday. It's sum over omega of Px omega, which is the sum over omega P of x given omega P of x. Right? So, no, very good question. So, you're very correct to say that this is something that we might find interesting, right? Because we are conditioning our observation, okay? So, intuitively it makes sense. And this thing can be calculated from these things that you know, okay? Via Bayes rule and marginalization on the law of total probability. Okay? Very good. Okay. So now, one way of finding the best strategy would be, best decision rule to be just to consider all possible decision rules. How many are there?
3.
Assuming what? Okay, let's make this concrete. Let's say we have 3 observations and 3 actions. So it was coat, home, umbrella. Okay. So how many decision rules do we have? So we can choose for every observation. We have 3 possible actions, right? So it's 3 times 3 times 3, right?
It's not 9 decision rules.
Sorry? Not 9, 27.
No, but why decision rule is 1 or 3, not you have many actions, but not.
No, so for every a decision rule would be if it's stormy, take a coat. If it's sunny, go home. If it's cloudy, take an umbrella, right? That's one decision rule, okay? So the way of specifying decision rule is choosing out of 3 actions, for each observation, choosing a particular action, right? So how many ways of doing that? 3 times 3 times 3, right? Okay. So, okay, this simple example, you could just iterate over all possible combinations, right? So, and for each such candidate decision rule, go and calculate this thing, which I said you could calculate, and just find the optimal one, right? The one with the minimum cost. But that's, in this example, it's, I mean, in this case, it's silly to actually do that, and generally it would be hard because you might have like a very large number of possible strategies. So there's a simple solution that I guess some of you have already alluded to. So I will tell you what it is. Before that, I will say that the optimal decision rule will be denoted by delta star. Okay? So star is usually used to denote optimality or something good about it. Okay, so let's say intuitively what you guys said. So you see the observation, okay, and you want to know what to do, okay? So what seems to make sense is to take the action that given this observation is what? You see an observation sunny, and you want to know what is the best, what is the action that I should take, given that it's sunny. Okay, that's what we're asking, right? What is the best action to take, given that it's sunny?
One with smallest value sum.
Response value
Right.
multiplied probability.
Right. So okay. So the intuition is correct. So you would want the action that results in a minimum cost, right? But there's a problem. Right, because there's uncertainty here, right? If you, let's say it's sunny, okay, and you wear a coat, is that all, will you always incur the same cost? No, it's a random thing, right? Because it depends on what? On the world state, right? So it seems plausible that what you want to do in order to figure out the best action given an observation is to consider the expected cost given this observation for each of the actions and take the action that what? That minimizes that cost. Okay? So, very reasonable, and indeed that's also the correct answer. So let me just define one thing before we specify the answer. So we define the expected cost of action alpha given observation X as well, we will denote it by R of alpha given X. Okay? So this Itamar is writing, so it's not complaining. Good. So I need to take the expected value over what? What is random here? The world state, right? We said before. So I'm taking the expected value over omega, P of omega given X, and the cost of alpha given omega. Okay?
This time we're conditioning.
What?
This time we're actually conditioning.
Yes, that's true, but this is not a condition on probability. Right. Okay.
But
Yes, this is for a particular X. Okay? So, this is a number. For every action and observation, this tells you if you were to play that action given that observation, okay, this is your expected cost. Okay? Sometimes you will pay lambda alpha given 1, sometimes you will pay lambda alpha given 2, right? Because the world state is not determined here, right? It's still a random thing. But this is the expected value. Yeah.
Can you try and demonstrate that on the example we're
Sure,
using?
yeah. So, let's say, what is the risk of a alpha, let's say, being a coat? What is the risk of wearing a coat given that it's sunny? Okay? It's, we have to sum over world state. So it's P of, so world state is rain, no rain, right? So it's the probability that it will rain given that it's sunny times the cost of wearing a coat given that it rains plus the probability that it will not rain given that it's sunny times the cost of wearing a coat given that it doesn't rain. Okay?
So again, it's not probability, it's just...
This thing here is a number. Yeah.
There is no probability anyway.
These are probabilities. These are probabilities. Okay? It's again, it's the expected value. It's in terms of units, it's in the units of costs, right? But you're just taking its expected value. Okay? Is that clear? Okay. So it's again, the mental experiment you're doing here is that you're conditioning, you're saying, out of all the sunny days, if I now focus on sunny days, okay, and in those sunny days I say I always wear a coat, okay, what is the expected cost that I will pay, okay? So in order to take expected cost, you have to sum over the random element, and that's the worst case. Okay?
So you're checking all the possible situations.
Mm-hmm.
Actions.
No, he's talking about this. I'm considering possible worst states. I ask, okay, so given that this observation happened, there is this omega in the background, okay?
This is observation. So you're like holding the observation and you're
I'm fixing it, yes, that's right.
All the situations around.
Right, I'm conditioning on it, okay? Okay? So this you can also think of as the expected value of the random variable lambda of alpha given omega, given that x has the value x. Okay? So this is, I mean, if you've probably seen conditional expectation, right? So that's exactly what we have here. It's the expected value of this cost function, the one that we keep worrying about, given a particular observation. Okay? And for every combination of alpha and x, there's a number here, right, that you can calculate. Using, I mean, all these things here. Okay, this goes back to your question. We have P of omega given x here, right? Okay? So that was not given to us here, but here is how you calculate it, right? So you can calculate P of omega given x from your problem data. Okay? So again, for every combination of alpha and x, you can calculate this number. Okay? Right. And this is called it's called the conditional risk. Okay, which is the risk, the expected risk conditioned on an observation. Okay. So now, if you see this thing, you have an observation, and you wonder which action should I take. What is
Can you repeat please the definition of
this? This?
Yes, the
I said
condition risk.
R of alpha given x is the conditional risk. It's called the conditional risk. Okay? Alright. Okay. So, it seems to make sense that if you want a good strategy, what you should do is for every x, take the action that gives you the minimal expected risk. Right? Conditional risk. Okay? It seems to make sense, but we've already committed to what we think is the optimum strategy, right? We said the optimum strategy is whatever minimizes the overall risk. Okay, so now I want to convince you that this is indeed what I just suggested, minimizes the overall risk. Okay?
Why it's not the same?
Sorry?
Why it's not the same?
It is the same, but I have to show it to you. Okay, so we should be very careful about saying that things are correct or equivalent without actually proving it formally. Okay? And it is a very simple result, but I want us to educate ourselves to sort of prove things formally. Okay, so here's well, I call it a proposition here because really not deep enough to call it a theorem. So I will say that delta star of x. So delta star is this thing, right? Okay, it is the optimal Bayesian decision rule in the sense of minimizing the overall risk. Okay, so this is a well-defined quantity, right? Given these that we define the problem, there is a delta that attains the minimum risk. Okay, and my claim is that that equals R mean over alpha of R of alpha given. Okay, so in words this says again what was sort of intuitively obvious to us from the beginning, that the best thing you can do given observation when you see an observation X is to take the action that minimizes the conditional risk.
What does it mean R mean alpha?
It means that so you can calculate for a particular value of X, so that's fixed, right? It's here and here. Okay, so let's fix
So I know the
x.
process, I just want to know, to understand the notation.
Okay, so I'll explain.
Argument.
Okay, so the argument says, okay, it's the alpha that minimizes this thing. Okay? So for example, if, let's say, x is stormy, okay? Let's say r of, so I calculate r of alpha given stormy. Okay? So what is that? There's r of coat given stormy. And let's say that's 0, r of home given stormy, 1, and r of umbrella given stormy is, I don't know, whatever, 0.5, okay? So I've calculated for every value of alpha, I've calculated this thing, okay? Now, what value of alpha minimizes this? Code, right? So the argument is code. Okay? So argument generally is when you take the minimum of a function over a particular variable. Argument is the value that gets the minimum. Okay? It's not the minimum value, it's the minimizer. Okay? Yes.
We said delta star was delta that minimizes the overall risk, right?
That's right. I defined it here. Okay. Okay. Yes.
Just to make sure, it goes back to a question we asked before.
Mm-hmm.
When you say our code when it's stormy, so you take equal 0.
Mm-hmm.
So you made a shortcut now, but you take into account that it was stormy and there was rain, and it was stormy and there was no rain, and the cost of the code.
Yeah, it's whatever I wrote on the previous board.
just to
Yeah, I didn't say. I mean, these are just numbers that I made up, but you
Yeah.
have to calculate them. So. Okay. All right. So let's prove this. Okay. So why is it a statement that could be true or false? Because this is for every value of x, this is a particular action. Okay, and for every value of x, this is a particular action, right? And I have to show you that they're the same. Okay.
It just depends on how you define optimal quantity.
Well, but I defined optimal here, right? So if I did, okay. Okay, so let's prove. So what do I need to show you in order to prove this? I need to show that any other delta that is not this delta star has what? Has worth higher cost, right? So we need to show that any other delta has same or higher R delta. Okay? Or in other words, namely, we want to show that R of delta is greater or equal than R of delta star. Okay? So let me do it this way. I think I can finish before. Yeah, maybe. So R of delta is sum over x and omega, p x and omega, R of not R, lambda of delta x given omega, right? So I'm going to break this down now. I'm going to sum first over x's, and then I'll write p of x here, and sum over omega, write p of omega given x, lambda of delta x. I'm sorry, of delta x given what? Given.
I think there is a step missing. You can break down without.
No, this is true, right? Why can I do this? Because p of x times p of omega given x is, what is that? P of x and omega, right? Okay, so and this is true because of this right here, okay? Well, the other way. Okay, what is this thing? What do we call this? R of, so this is sum over x, P of x, and this is the R of delta x given omega, right? Correct? This is just a definition that we had on the board before. It's the cost given the expected risk of taking action delta x given observation x. Okay? Now, by definition of this delta star, what do we know about the risk of delta x compared to the risk of delta star? It's greater, right? So this is greater than sum over px r delta star x given omega.
Should be given x, right?
Sorry? Given, yes, that's right. Okay?
Why would you concatenate them to every x? Because they don't influence each other.
You're right. That's why the proof will work. Okay? I haven't done anything wrong. It's just it's sort of obvious to you that I could do it independently for each x, right? But that's exactly what I do. For each x, this is correct, right? Okay? And that's why I can write it. Okay? For every x, it's true that delta star has a lower conditional risk than delta. Okay? So I can do it in the sum as well. Okay? So there's nothing wrong here. Okay? And what's this thing equal to? So look, this is R of delta here, right? This is R of delta. So what is this thing? It's R of delta star, right? So that's what we want.
This is what we need to prove because earlier I didn't understand what we need to prove. That's the tautology.
No, but look, it's a proof, right? This is the proof. This is the proof that this delta star defined in this way, okay, has a better overall risk. This one has a better overall risk than any other delta. Okay? So my claim is that delta star defined in this way has a better risk than any other delta, which I just showed you.
By definition.
No, it's not true. I claim it.
Mean.
Okay, let's. We can take a break and I'll come back to it. But it is a proof. I mean, it is a sequence of logical steps, right? Okay. יש הגדרה אחת של דלתה סטאר שאומרת זה הדלתה שממזערת את הדבר הזה, אוקיי? אוקיי. מה זה ברור? ברור זה צריך להוכיח. אז פה אני עושה הגדרה. לא, זה לא, בהגדרה זה מה שממזער את זה. אוקיי? אוקיי, וזה כאילו, זה, הדלתה שזה הדבר הזה, אוקיי?
הקיום הזה להוכיח זה המעבר מהיחיד, כאילו מהיחיד לכולם?
אמרתי, זה מאוד פשוט. אבל זה אני יכול להראות.
יכול להראות איפה השתמשת? עובדה שבדלתה סטאר X שווה ארגמן.
כן, פה. שמעתי לכל X עבור ספציפי, נגיד עבור X שווה 2, זה מתקרב.
ולכן לכל שכן עבור הסכום.
עבור כל אחד בנפרד ולכן עבור הסכום.
בכל למדה אתה מתכוון בעצם X. עוד שאלה. זה לא באמת, אוקיי, איבדתי שלך עוד הרבה נקודות, אז נתחיל מזה שאני לא מבינה למה דלתה X משתנה. כאילו אני מבינה שהוא פונקציה של X ו-X משתנה בכלי, אבל הוא פונקציה מ-X ל-A.
נכון. אבל האקשן שאת לוקחת, הוא עצמו משתנה מקרי, כי הוא פונקציה של משתנה מקרי.
אוקיי.
הפעולה שאת...
A מוגדר לי כזה?
כן, אפילו לא רציתי לקרוא לו, בכוונה לא קראתי לו A. הדבר הזה, דלתה X, בוא נקרא לו Z, אוקיי?
כן.
Z שווה לדלתה X, הוא משתנה מקרי.
כן.
ופה זה לא באמת, כאילו זה לא באמת שזה לא...
זה הגודל שהגדרנו אותו מקודם, זה התוחלת של הקוסט שתהיה לך אם תצטרכי את הפעולה דלתה X בהינתן שהאובזרבציה X.
אוקיי, אז זה בעצם...
זה מה שהגדרנו מקודם.
התוחלת בהינתן X, זה X גדול.
זה X קטן, כולם קטן. ברגע שיש סכום, זה כאילו כבר עוברים על הערכים של המשתנה.
אוקיי, עוד שהכלום, כשאתה כותב את זה, זה X גדול.
כן, אם אני אתייחס אליהם כמשתנים מקריים, אז זה לא לערך ספציפי שלהם,
אז זה גדול.
ואיפה אנחנו שזה...
זה ההגדרה של ככה הגדרנו את R של... R של אלפא בהינתן X, או סופרים על אומגה, פי של אומגה בהינתן X, למדה אלפא בהינתן אומגה. כן, ככה, אוקיי? אז נקרא את זה פשוט אלפא שווה לדלתה X.
אפשר לחשוב איכשהו על איזשהו מקרה הנחות יסוד של העולם שבו זה לא יהיה נכון?
לא, זה נכון כאילו מתמטית.
נכון, אבל זהו, כאילו זה איכשהו זה
אתה יכול לחשוב על מקרים שבהם האסטרטגיה שזה יציע לך, היא לא תהיה אינטואיטיבית, היא לא תהיה פלוזיבל באמת. אוקיי? למשל, המקרה הכי פשוט זה שיש, נגיד, באובזרבציה מסוימת יש פעולה מסוימת, שאומנם האקספקט שלה הוא נמוך, אבל יש אינסטנס מסוים שבו אתה... כן, אלא באמת, אם הקוסט הזה היה אינפיניטי, אז גם הריסק היה אינפיניטי. אוקיי, לא, אבל יכול להיות שזה אנשים שמוות זה גם, זה קוסט 1000 בשביל, אוקיי? אבל באמת, במילים אחרות יש מקרים שאתה רוצה לא למזער את התוחלת של הריסק, אלא את הריסק הכי גרוע.
לא, אבל חשבתי דווקא על זה, השאלה למה צריך להוכיח את זה, זה כל כך פשוט, כאילו אם לכל אקס אתה עושה מזה, זה בחור שעשית מינוס את הכל.
זה באמת נכון, תחת הקריטריון הזה, שבעצם ברגע שאתה רואה שהאקספקט, ה-R דלטה הוא פשוט אפשר לכתוב אותו ככה, אז זה ברור שאתה צריך למזל כל בנפרד.
כן, אז זהו, זה... שהוא...
זאת אומרת, אין... ברגע שהפעולה שלך היא מותנית על האובזרבציה, ואתה רוצה למזער את התוחלת, אז זה ברור שמה שמנת לך זה תוחלת בהינתן האובזרבציה, כי האקשן באמת תלוי באובזרבציה, זה דבר אחר, לא משנה. זה מה שאתה מקבל, זה מאוד הגיוני, אז פר זה שזה הדבר שאתה רוצה לעשות, זה הדבר שאתה רוצה למזער, זה הדבר שאתה רוצה לעשות. זה מה שיפה בהסתכלות הביציאנית, שזה נותן לך תשובה זאת אומרת, זה קריטריון שהוא סביר, אני נותן לך תשובה פשוטה, אוקיי? אז עם מה אפשר להתווכח פה? או עם הקריטריון, שבאמת במקרים מסוימים אתה רוצה להיות זהיר ביחס מיני דברים, או ההנחות, אוקיי? ההנחות למשל שאתה יודע את הדברים האלה. כמו שאמרת, יכולים להיות כל מיני קריטריון שלך, יכול להיות יחסי, אפשר לחשוב הרבה דברים בכל התחומים שמתעסקים בדברים.
שזה כוכב של X מוזר היטב, אז כאילו זה לא היה פורמלי יותר אם היית אומר שאם היית טוען בטענה של יחיד, עד את הכוכב הזה?
כן, כן.
ואז היית מראה שכל אחד אחר הוא גדול ממש.
כשכתבתי את זה, היה אפשר לעשות ככה, להגיד... היה בעצם צריך להגיד דבר כזה, דלתה, נקרא לו דלתה בר, נקיים עבורו דלתה בר, תגדיר דלתה בר ככה, אזי דלתה בר הוא הארגמין של R של דלתה. זה היה יותר נכון.
וכאילו שהוא היחיד גם, שאין דלתה.
לא,
זה די ברור
כשאני מגדיר את זה ככה, לא, דווקא לא צריך להיות יחיד. יכולים להיות כמה... תחשוב למשל שהקוסט שלך הוא 0, שכל הלמדה שלך הוא 0, לא משנה מה, אז זה לא משנה גם מה תעשה, ואז כל פעולה שתעשה, כל כלל ההחלטה שלך הוא אותו... אז זה באמת יותר נכון, גם תכתוב כזה הפרעות, זה להגיד בכך. כשאתה אומר דלתה סטאר, זה באמת יוצר איזה רושם שכאילו יש אחד כזה.
פה זה בעצם הסיכון המינימלי.
של מי? דלתה סטאר זה הסיכון המינימלי.
הסיכון המינימלי שבכל מקרה אלי, אז הראינו שהסיכון שאנחנו חשבנו קודם יהיה יותר גדול מהסיכון המינימלי?
כן. לכל דלתה, אם אתה זוגף איזשהו כלל, אוקיי? הסיכון של הכלל הזה הוא יהיה יותר גדול מהסיכון של דלתה סטאר שמדבר כאן.
שאליו אנחנו רוצים להגיע.
כן. ברור? שוב, בוא נגיד את פשוט. יש דלתה סטאר, אני מגדיר עכשיו דלתה סטאר. כלל שאני קורא לדלתה סטאר. זה כלל מסוים, נכון? בכל X, אתה הולך, חושב את הדבר הזה, מוצא את האקשן שהכי טוב. זה כלל הפקה מסוים לבעיה. עכשיו הטענה היא שהוא יכול כלל אחר שתיקח, כל כלל. הסיכון הכולל שלו יהיה יותר גדול מזה של דלתה, אבל לכן דלתה סטאר הוא הכי טוב.
עכשיו בעצם כשאני מריץ את זה, אני מקבל בסופו של דבר, קבלה לי טבלה של קוש, ואחרי שאני מריץ את זה, אני מקבל עוד טבלה של מצב ואקשן.
כן, זה החוק שלך, זה הכלל, כלל החוקה.
אז בעצם אני יכול... פה? את יכולה לחשוב בתור
כל הצמדים האפשריים של X ואומגה. כל הצירופים האפשריים של זה וזה. כי כל פעם שמגבילה משהו, הדרך המלאה לתאר אותו זה מה האובזרבציה ומה זה מכיל את כל מה זה הסמפל. זה בעצם משהו שאמור להכיל את כל רכיבי האקראיות של הפיתוח. את כל התוצאה של כל חזרה של הניסוי בעולם.
תודה.
שלי קצת? כן, טוב פשוט.
זה יותר לי חלט.
מעולה.
אז מה פה הנקודות העדינות? אני תמיד מחפש נקודות העדינות.
קודם כל יש עניין של...
לא בהוכחה דווקא, בסטינג, כי אתה מניח פה המון דברים, נכון?
אוקיי, כן, אז יש... למה זה לא מצמד...
למה זה לא מעניין? למה זה לא מעניין?
זה דווקא כן מעניין. אבל זה לא...
לא, זה מעניין מתמטית, אבל זה לא מעניין.
לא, זה גם מעניין כל
כן?
כן. המערכות שעושות החלטות אוטומטיות שעושות החלטות בנוסחות הדברים.
אוקיי.
עכשיו למה זה לא תמיד עוזר לך בחיים, ולמה אי אפשר להשתמש בזה לפתור כל בעיה? כי לכאורה זה כן, הקריטריון עצמו הוא לכאורה סביר, אוקיי? הפיתוח הוא סגור.
אתה אומר קריטריון למה אתה מתכוון? המינימום או זה?
זה שאתה מחפש את הכלל שאני מגר לך את האוברול, אוקיי? אז השאלה א' אם אתה מסכים לזה, וב' אם אתה מסכים להנחות שיש. אז פה זה הבעיה. א', למזל את האוברול זה לאו דווקא משהו שבני אדם. כי אנשים הם עושים ביחס לסיכונים תוצאות קיצוניות. למשל, אם אתה שם 1,000 שקל בבנק, אתה לא רוצה להפסיד הכל. זה, למרות שזה להפסיד 1,000 שקל, זה מבחינתך הרבה יותר גרוע מאשר להרוויח.
לא, אבל אז זה גלום בפונקציות המשקל שאני מכן.
לא, כי אתה יכול להגיד, יכול להיות שההסתברות שזה יקרה היא מאוד נמוכה.
אבל זה יותר...
בתוחלת זה מורה עם הסתברות נמוכה, ולכן זה ישפיע מעט על התוחלת, ולכן יכול להיות שאתה תבחר באסטרטגיה שהדבר הזה יכול לקרות בעיקרון.
זאת אומרת שיש מצבים שזה לא מגולם בתוחלת, אבל מבחינה האנושית זה כאילו no way.
זה מגולם בתוחלת בגלל שזה מכפלה של קוסט בהסתברות. זה כמו הוכחה של פסקל לקיום המקרים האלה. אולי זה בהסתברות מאוד נמוכה, אבל הקוסט הוא אינסופי מבחינתנו. אוקיי? אז עכשיו זה דווקא, זה יותר מתאים לתיאוריה הרגילה. אבל לא, זה לא. בגלל שמבחינת, אם ההסתברות למשהו היא נמוכה, אפילו אם הוא גבוה, הוא נבלע בתוך ההסתברות,
זה לא טוב.
אז בכלל, אתה עשוי לבחור באסטרטגיה שאתה תספוג את הקוסט הזה, אוקיי?
אבל אתה
אם אתה
אומר...
מאוד מפחד מקוסטים גבוהים, אז...
זאת אומרת, זה לא תמיד יהיה פרקטי, כי זה גולם, זה מאפשר התייחסות למקרים זניחים עם קוסט מאוד גבוה.
זה לא פרקטי, תראה, אנשים נגיד משקיעים יותר אמיצים, כן? הולכים ללמוד אסטרטגיה שיש בהם ריסק הפסד יותר גבוה, אבל עם תוחלת יותר נמוכה שלו.
בסדר, תגיד אותי מה אני טועה, לא כל זה מגולם תביא לי את סטאק הערכים שלך, את הקוסט שאתה רוצה, ואני אבנה לך...
זה לא מגולם, בגלל שבמקרים האלה, אפילו שאני יודע לך משהו שהוא ממזער את ה-overall risk, אחרי שאתה תשחק עם זה, ופתאום מגיע מצב שישחק את כל עומך, בוא תגיד לי מה זה בליגוד דבר הזה. אני אגיד לך משהו, התוחלת זה יותר גמור. זה לא שנתי שקרה המאורע אחרי.
אז יש לך עוד וידאו כזה שאומר...
נכון, בשביל לעשות משהו שהוא אופטימלי במובן של היזהרות מסיכונים, אז צריך לעשות משהו אחר.
זה כבר מודל אחר לגמרי.
אתם תראו את זה. זה מינימקס, יש קריטריון של מינימקס אופטימלי. זה הדבר הכי גרוע שיכול להיות. אבל זה דורש...
אז אני חוזר לשאלה מפה, אז מה הנחות?
אוקיי, אז משהו יותר חמור פה, שלרוב, שני העולמות האלה, גם האומגה וגם איקס, הם משתנים מאוד, בממד מאוד גבוה, אוקיי? יש לך המון אובזרבציות, יש לך רבות אובזרבציות, ואתה לא יכול לדעת את פילוג הזה כפילוג רב-ממדים, זה שאני יכול לעמוד אותו.
אתה לא יכול לדעת לך על איזה התפלגות.
כן.
זה מה שחסר לנו בעצם. כאילו, גם אם ההנחה נכונה, אין לנו את האובזרבציה. ואז מה שאתה עושה, זה רק...
זה כבר סב אופטימלי, בגלל שההנחות שאתה מניח הן כבר לא נכונות בעולם.
אתה מופיע בגלל שהם עושה את כל הדאטה.
את כל כן, התפלגויות,
בהינתן אוסף סטאוטים, בהינתן שיש לך היום את כל ההתפלגויות בלה בלה בלה, יש לך מערכת מאוד פשוטה שפותרת עושה למידה, אין כבר עדיין למידה?
נכון, למידה לרוב התייחסו ללמידה של התפלגויות האלה.
אז זה הלמידה, ללמוד את ההתפלגות שחסר לנו, כי את הפתרון האופטימלי אפשר לזה.
אם אתה תחת הפתרון הזה.
אבל למידה לא תהיה פה בלופ.
אפשר לעשות עוד, אני מדבר על למידה שהיא גם וגם ללמוד את הדברים האלה, שגם יכול לחשוב על זה כסטים של קבלת החלטות. אתה רואה דאטה, אתה אומר, אז זה אתה לא תשלם לי אף שילוב הקיים. All right, so let's continue. Okay, so this is the nice thing about, let me say what's good and bad about this theory. The good thing is that given that you make these assumptions and that they are reasonable, and that you agree that this is what you want to minimize, which is also sort of reasonable, you want to minimize the amount of the cost over time. This tells you there's a very simple solution to this problem. Okay, so that's the nice thing about the Bayesian framework. It makes certain assumptions, but then from these assumptions, your optimal behavior follows. Okay, which is good. You won't get to see so not many nice solutions to decision problems. Okay, so that's good. What's bad? First is that you need to know this distribution. Okay, so imagine x is a vector of let's say in terms of weather, it's 100 things you can measure about the weather, the temperature in different places, the humidity, etc. To figure out the distribution of these variables given a world state is hard. You need a lot of data to collect it, and it becomes practically impossible if you want to consider a very high dimensional observation. So that on its own is enough to make it impractical. And the other thing is that this expected overall risk is something that might not always be plausible. For example, there might be certain scenarios where you incur a very high cost. Okay, let's say you lose all your money or you suffer a little stroke. That happen with very little probability, but for you they are unbearable. Okay, so if you look at the expected cost, someone tells you, okay, you might die, but it's like these little things that you sign in diving courses or whatever. Okay, there's a risk of death for any medicine that you take, but it's with very high, low probability. Okay, so, but in these cases, for us humans, it's not necessarily the sensible thing to do is to take expected values of it. Okay, because we really want to avoid a particular situation. Yep.
You can assign a really big cost.
You could, but that might not be enough, even if it has a lower probability. So you're right that if it's infinite, you might avoid it. But in cases where you want to say minimize the worst case thing that can happen to you, then that requires a different strategy, and we'll talk about that as well. Yep.
Just one question about your proof. You wanted to prove that delta star of X is always smaller than any other delta of X, right?
That's right.
But in your proof, you use the fact that delta star of X is minimal. I mean, you use what you...
No, I use this definition. All right, so there is something a bit... I should have stated things a bit differently. I should say delta star defined in this way. Okay? This would be a clear way. Let's say you define delta star as this. Okay? So let's say if delta star is defined this way, then R of delta star is less than R delta for all delta. Okay? This is clear. You're right. And there's another subtle point that someone asked about. What if I have? What if this minimum is not unique? Okay? Then that's fine. It just means that there are multiple optimal studies. Sorry?
Then you don't know what to do.
No, it just means that it's the opposite. There are many optimal things that you can do. So let's say, for example, that lambda is always 0. For all actions in all world states, it's 0. So what's the optimal thing to do? Everything, right? It doesn't really matter. Okay? So it's like the Zen policy, or the Taoist. Not one of those. Okay, good. So I want to take a specific simple example and show you how this works. That it makes sense. It gives you a sensible strategy. So let's take something like a digit recognition problem, where let's say X is an image, and omega is the digit described in the image. Okay, so I have in my mind an omega, which is what I want to, the digit that I want to draw. I won't tell you what it is. I'll show you X. Here's X, okay? And now what's your action? Tell me what the digit is, right? Okay? Well, that's a sensible game, right? Okay? So, again, so omega is sort of the correct label of this X, okay? And we're playing a game where your action is to tell me what I do, okay? What the digit is. Fine? Omega is the digit described in the image.
Basic observation
Yes, yes, I'm keeping the right notation. Okay. So this is a sort of a classification setting or a labeling setting, and your action A is to say which digit is in there. Okay, so there are really two things here, right? One is the true thing described in the image, the thing that I meant, okay? And the other is what you say is in there, right? Okay, so now, in order to play the game, we need to decide on how bad you feel when you say it's a 6 and it's actually a 7, okay? So what makes sort of sense to do? So you pay 1. Okay, you pay 1 shekel for every mistake.
For every kind of mistake?
Sorry?
For every kind of mistake?
Okay, so that's another decision to make, right? You might say, okay, if it's a 6, if I wrote a 6 and you say it's a 4, you don't feel so bad about yourself because it might be similar, okay?
But if it's a 9, then...
Yeah, so you could do that, but we'll stick with the sort of, classic approach of saying that lambda, okay, the cost will be, so we'll put it as, okay, so for here we'll have 10 world states, omega 1 to omega 10, and here we'll have 10 actions, alpha 1 to alpha 10. Okay? So, I want to do, yeah, I'll do it actually. That's the way we do it. Okay, so I just describe the 10 actions by alpha 1 to alpha 10 and omega 1 to omega 10. Okay? And then the cost will be lambda of alpha I omega j will be 1 if I is different from j and 0 otherwise. That's right. Okay? So basically every time you make a mistake, I say you made a mistake. 1. Okay? Okay. So it's already useful to know that the expected risk, or let's say the overall risk of a particular decision rule theta, delta, is, what is it? Well, it's the expected error probability, right? Okay? It's just the expected probability of error. I mean, I think it's sort of obvious, but we'll also show it more from it. Okay? All right. So you can even ignore this for now. Okay, so we have a whole the Bayesian decision setup. Let's assume that I know these things as well. So what is P omega in this case? What does it mean? It's the prior over this variable omega, the world state, namely the digit, the identity of the digit that I draw. So what would you think this would be? Well, it depends, right? If I play a game where I draw these digits uniformly, then it would be uniform, right? P of omega would be 0.1 for each one of the digits. But we might play a game where I focus on 4, 6s, and 8s, right? Where I just decide to play these, and then P of omega would have a high probability for those. Okay? So let's for now assume that this is the cost function, and these are, we know these. So you already see how maybe absurd assuming this thing is, right? Because it means that you know the distribution, the probability of seeing every possible image, given, say, that I'm drawing a 1. Okay? So it sort of means that you know all my 1s. Not only do you know them, you know the relative probability with which I'm going to draw a 1 like this or a 1 like this. Okay? So that's assuming quite a lot. But let's assume it anyway. Okay.
All right, so now I want to ask what's the optimal thing to do. Okay? So when you see, after you see X, after you see my image, what will you say the image is? Okay? You want to guess? Okay, that's true. So I want to find the optimal policy for this case, so the optimal decision rule. So we know that the optimal, we want the optimal decision rule. So what is the optimal decision rule? It's the one minimizing the conditional risk, right? So given observation X, which is the digit that I do, the optimal decision is to choose alpha minimizing R of alpha given X. Right? That was what we said before. Right? Okay, so let's just calculate this R of alpha given X for all possible. So X is fixed, right? I drew the digit. Now you just have to calculate this thing for all alpha values and choose the alpha that minimizes it. Correct? Okay. So what is R of alpha I given X? What particular I? Let's write it. According to the definition, again, it's expected risk over, when I'm taking expectation over the thing that is still random, which is the world state. I'm asking what's the probability of the omega given X times lambda of alpha given omega. Okay? Now, okay, so what is this? What's this thing? This is alpha I, right? Okay. So alpha I given omega is what? It starts with 0 or 1, right? When is it 1? Almost always, right? For all digits that I drew, you're going to make a mistake, except one, which is the correct one. Okay? And which one is the correct one for alpha I? Omega, right? So I'm going to, so that's the only case where I get a 0. Otherwise, I get a 1, right? So I just need to sum over all omega, over all j not equal I, T of omega j given it. Right? So I sum over all the digits that are not the one corresponding to this action. Okay, so there's a nicer way of writing this. Okay, no, this is the sum over this probability of omega given X for all values except 1. Right? So if I summed over all j's, what would happen? 1. Right? So this is the same as saying that 1 minus p over omega I given X. Okay? Yep.
Just due to the fact that we chose 1 shekel as a price?
Yes, that's right. Otherwise, it would have been
multiplied by 2.
Yes, that's right.
You can take the scalar of that.
Yeah. So, but it would multiply everything. So it wouldn't affect. Actually, as long as you put the same number here, it's going to be the same strategy. Okay, you can convince yourself of that. But if this starts being variable, then no. Okay.
Can I ask a question?
Yeah.
Shouldn't be j equals I?
No, because here all the ones that where the lambda is 1 are the cases where it's not equal.
Oh right. Okay. Yeah.
Okay. So we can say then the optimal. Okay, so now I have to go over all I, and for each I look at R alpha I given X, which is just this thing. Okay. So what is the I that minimizes this thing?
There is no I, we know.
You know these things, okay? Okay, so right.
So it's the one where this probability is maximum, right? Because then it has a minus here, okay? So the I that maximizes this is the I that minimizes that, correct? Okay. So the optimal omega, how do I write it here? The optimal alpha. I'm sorry. The optimal alpha is let's call it alpha I star, such that I star is the arg max over I P omega I given. Okay? It says if you see an x, what should you do? You should go over all possible digits, ask what's the probability of this digit being written given the image, okay? And take the one that is most likely. Okay, if you had to guess, this is what you guess, right? Okay, you want to guess what omega was, so just take the one that's most likely.
This is a very trivial conclusion.
But it's true. Well, I mean,
that's the goal of the game, to try and identify.
No, but this is a very well specified answer, right? If you know these probabilities, which you do by our assumption, okay, you could go and calculate these, okay? You have to consider 10 options. You calculate P of omega 1 given x, which is sort of the probability that I meant to write a 1 given that what I do, okay? P of 2 given x, P of 3 given x, P of 9 given x, okay? And you choose the one that is maximum. So this is an algorithm, right?
The conclusion intuitively, the instruction is just specify the image which is most likely to be the image drawn from the...
Okay, but it's more or less what you said, okay? But one, we've now convinced ourselves that it's the optimal thing to do.
Mathematically.
Yeah, and the only problem is that you don't necessarily have these distributions. So if you had them, this is the optimal thing to do, okay? Maybe it's obvious to you in retrospect, okay? But it's reassuring to know that this is the optimal thing to do if you want to minimize the course points that you pay, okay? All right? Yes.
So actually this method advises us to find a specific digit and hold on to it.
No, given an image.
Okay.
Given that, okay? So it works this way. I show you this thing, this is x, okay? And now you ask, what's the probability that of omega 1 given x, meaning that I meant to draw a1 given this. You go, and for 7 probably, or either 7 or 2, you'll get high probability. Okay?
But it's not just the probability of you drawing 7?
No, probability of my drawing 7 could be uniform, right? Because that's the a priori probability of me drawing a 7. If you don't know anything else, before you see this thing.
Prior.
Yeah. The prior on the digit that I choose is my, that's my business. This is whatever I want. I can draw these digits from whatever prior I want.
So this probability, if you give me a number that you always been drawing, what the probability would be anything.
Sorry? If I don't give you a number?
No, if you give, what is the difference?
Okay.
In Hebrew?
No.
What is the difference between the prior probability of you drawing 7 and the probability after you give me the drawing being 7?
Okay, so again, we are in the game where we assume we know these two things, okay? So P of omega is this prior probability of me drawing any one of the 10 digits, okay? And let's say we're in a game where I draw these uniformly, okay? P of x given omega is the probability of a particular image given that I chose to draw one, okay? Okay, so this links what I meant to draw to what I'm actually drawing, okay? Now P of omega given x is, I write it because it's instructive, it's P of, by Bayes' rule, it's P of x given omega I times P of omega I over P of x, right? Okay, so I actually meant to do this, so let me do it now. Sorry? Yes. Yes. So this is the arg max over I of this. Okay. All right. And now we see all our friends from there, right? And they're well separated. So we have P of omega I, which is the prior. Okay. P of x given omega I, which is the image given what I meant to draw. Okay. So you see how they're combined here. And there's also this P of x. But actually, does it matter, this P of x? Does it matter? It's just a constant, right? So it's a maximizing over I. Okay, so this is actually equal to the arg max of I, P of x given omega I times P omega I. Right? Because P of x is just a multiplicative constant, it doesn't matter. Okay, so that's further simplification that we need. Okay, now you see perfectly how these things are balanced, right? So this, we call this the posterior of the of omega given x. It's made up of how x is likely given, that this is what I meant to draw, times the prior probabilities that I do this. Okay? So if P omega is, let's say, uniform, meaning it has the same value for all digits, then the optimal decision is just to maximize P of x given omega I, right? Because in that case, if they are uniform, then this goes away, okay? And then I'm just left with that. Okay? And this is even more intuitive, right? It just says, what is the digit that I do? I'm just looking at going over all digits and asking which digit has the highest probability of generating this thing. Okay? Alright? So even more intuitive. Okay, so just in terms of terminology, this is called the maximum a posteriori decision rule. Okay? So this is max a posteriori. Why is it called that? Max because of the max, okay? Why is a posterior? Because I have my prior beliefs on omega, which is what I think before I see the image, okay? So before you see the image and I ask you what it is, you might say, well, if Amir doesn't have any affection to any particular digit, it's probably uniform, so I don't know, I have no idea what it is. And after you see the observation x, you can construct this thing, which is the posterior. Okay, it's the probability of omega given your observation. Okay, so it's like you revise the belief on what omega should be after having seen the observation. Okay. All right. Okay. So let's simplify things further. And let's call it, what do I call it? Error. So this setting is sort of error minimization, right? Is what we have in mind here, minimization. So I want to constrain it further and just assume we have two states. Okay. It just help us develop more intuition. Is this clear so far? So again, we talked about a game where actually your action is just to try to guess what the world state is, and if your guess is wrong, you have to pay 1 point. And we said, okay, the optimal thing in this case is to guess the state that has highest posterior probability. Okay? So it makes sense, and is the Bayesian optimal thing to do. Okay, so now let's assume that we have two states, meaning, so basically we assume A is just two states, alpha 0 and alpha 1, and omega accordingly is two states, omega 0 and omega 1. Okay? So the game is that, let's say if we want to stay in the digit example, I draw either a 4 or a 6, we know that this is the game. We announced it ahead of time, and you have to tell me what I do. Okay? But it's only going to be one of the other four. Okay? So it's just a restricted form of this game that we had before. Okay. So let's just recap what we said here. Given x, the observation, what do? We choose. I don't want to say it. Okay. We will choose alpha 1. Okay. When do we choose alpha 1? Look at it. When do we choose alpha 1?
When we think that when omega 1.
Right, when omega 1 is more probable than omega 0. Okay? So, given x, we choose alpha 1 when or if p of omega 0.
You assume the cost is the same?
Yeah, I mean the same setting as before. Okay? This is the subset of subsection of this. Okay? So I'm continuing with exactly the same setup, just I restrict myself to space in order to give more intuition. Okay. So given x, we choose alpha 1 if p of omega 1 given x is greater than p of omega 0 given x. Okay, this is just the same and same, right? So if I have an x, I will choose alpha 1 if omega 1 maximizes. Okay? Makes sense, right? Okay. So now I just want to rewrite this a bit to give us further intuition. So what does this mean? I'm just going to use the Bayes rule again. So this is p of omega 1 given x times p of x over p of omega 1 is greater than p of omega 0 given x times p of x over p of omega 0. And if I do some algebra, I conclude that this is the same as asking p of omega 1 given x, p of omega 0 given x to be greater than p of omega 1, p of omega 1, 0. Yeah. This side? No. Sorry? No, something is wrong.
Okay.
1 over 0. No, that isn't wrong. What? Take 1. Oh yeah. Okay. Sorry. Yeah, I knew this. Okay, sorry about that. There's many ways of doing Bayes rule wrong. So this is if given omega 1, p of x, p of x given omega 0, p of x. Okay, and then this is the same as p x given omega 1, p of x given omega 0, greater than p of omega 0, p of 1. Okay? Alright, so let's look at this for a second. So what we said there is that I will choose alpha 1, which is like saying the state is omega 1 if this holds. Okay? So let's consider some simplifying cases. Let's say the priors are equal. Okay? So 0.5, 0.5, which means I don't have any special prior belief on whether it's 0 or 1. Then what is this here? 1. Okay? And so if uniform prior, then let's condition is just P of x given omega 1 is greater than P of x given omega 0, right? Which sort of makes sense, right? It says I would choose to say that it's state 1 if x is more likely given state 1 than given state 2. Makes sense, right? Okay. But now let's assume the priors are not uniform, just so we understand the effect of the prior. So let's assume P of omega 1 is very small. Okay? Then, what do we have? We have the P of x given omega 1 should be greater than, let's say, P of omega 0 over P of omega 1, which would be what? What sort of number? Pretty large number, right? So let's say C times P of x given omega 0, where C is large. So why is this intuitively sensible, that this is what will happen? Why is it true that P of omega 1 is small? What does it mean that P of omega 1 is small? It means that a priori we don't expect the state to be 1, right? There's a low prior probability for that. Okay. So then this tells us, in order to decide that the state is 1, even though it's not likely to be 1 in advance, it's not very likely to be 1, you need probability of x given omega 1 not just to be larger than P of x given omega 0, but to be much larger. Okay? So it makes a lot of sense. It says if you your prior is that you don't think that dogs can talk. Okay, let's say you have to decide between dogs talking or not, and your dog calls. Okay, and you say okay, maybe it sounds a bit like a word. Okay, so the probability that I would see him coughing this way, given that dogs don't talk, is maybe so this is. Okay, let's say he coughs and it really sounds like a word, okay? So you say the probability that he would cough like that given that he speaks is pretty high, okay? He would be able to generate such a cough. But because you don't want to seem crazy, you say, okay, I really have to be convinced. It has to be much, much larger than the other probability for me to convince myself that it's actually that one is true, okay? So the prior acts sort of as a scale to gauge by how much the probability of 1 needs to be greater than 0 for you to actually make the decision that it's wrong. Okay? Make sense? Okay. So I advise you to look at these, whenever you get these decision rules, you should look at them at length and sort of convince yourself that they make sense. Try to consider different extreme examples, like what happens if this probability is very low, what happens if the prior is and this prior is low, or this prior is low, and just see that the story is sensible, because usually it should be. These rules don't usually give you something that's counterintuitive. Okay. So you will see several such examples in the exercise. I'll do one more for you. Okay. So let's say that x. Let's say that x is in the real, okay? I don't know, let's say you have, right, okay, you wake up in the morning, you measure your fever, okay? So that's your observation is in the real, and you want to know if you're sick or not, okay? So omega is I'm sick or not. So omega is sick. The other one, healthy. Okay?
You need to restrict the rate of x. No, because if it's the entire real numbers you have difficulties minimizing function later.
Okay, I'm going to make some assumptions. Okay. So now I want to. So now in order to play this game, what do you need? You need the prior of you being healthy or sick, which maybe you have. Okay. So there's a higher chance that you're healthy, I hope. And you need this thing. What is this? It's the probability of having a particular temperature, given that you're healthy, and given that you're sick, right? So we need the following distributions: P of x given that you're healthy, and P of x given that you are sick. Okay? So let's assume that these distributions are, what's the simplest distribution on continuous variables that you know? No, uniform on continuous is not that simple actually. What's uniform on the entire line? Yeah, it's a bit tricky, right? So I would say the simplest is Gaussian, but okay, it's in the eye of the beholder. It's certainly the easiest to manipulate, okay? So let's assume they are Gaussian, so both are Gaussian, with variance 1 and mean, let's call this mean mu h and mu s, okay, for expected temperature when you're healthy and when you're sick, okay? So if you want to think about it, let's draw it. So if this is x, so you have two Gaussians. One is when you're healthy, so this would be mu h equals, what is it? 36.7. So this is P of x given healthy. And then there's, I don't know, what do you think it looks like? Maybe like this. This is 39. This is P of x given. Okay? So now, you have all the tools to decide if you're sick or not. You just need to check, like we figured this out there, right? What is P of x? You need to look at P of x given omega equals, what do you want to decide if you're, let's say this. P of x omega given s equals s, P of x omega equals h, whether that's greater than probability of h over probability of s. That's right. Probability of omega equals h over probability of omega equals, right? So decide s if this is true. Okay? What do you think you're going to do? What's the optimal thing to do? Let's say assuming equal priors. Okay, I'm going to tell you. So assume P of h equals P of s equals 0.5. So this goes away, right? It's just 1. And now we have to compare these two things. Okay? So just recall that the Gaussian, so P of x given, say, omega equals h is, by the fact that it's Gaussian, is 1 over square root 2 pi, and the variance is 1, so it's minus half x minus mu h squared, right? Yes.
And I get it from this one. That's not the, that's the density, that's the probability.
Okay. So this is right. This is the major notational crime that I'm going to make in the course. Now we'll call density P as well. Okay. If it's too much for you, this is the time to change it. Okay. The reason I'm going to do this is that usually I want to do things that handle densities and probability methods in the same.
Likelihood.
Okay. So yes, this is the density. Okay. I'll consider changing it at this point, and then I will. Okay. All right. So it's easy because you have things in the exponent. Turns out that it's easy instead of comparing the probabilities to compare what? Log probabilities. Okay. So this is the same as that as saying log P of x given omega equals S is greater, again, I'm in uniform priors, log P of X given omega L. Okay? So, and then there's a bit of algebra. If you write this thing and you do the algebra, turns out that this is equivalent to X being greater than mu H plus mu S over 2. Okay? And this only works if you assume that mu H is, mu S is greater than mu H. Otherwise, it's the other one. Okay?
What did you ask before?
About, okay,
no,
so about this?
You compare the pinpoint value, but you need to integrate from minus infinity to this value or something.
No. So in all this theory, I can replace wherever I say P. Okay, if X is continuous, then P means the PDF of X. Okay, so I mean PDF is the same as a discrete distribution. I mean it's equivalent of a discrete distribution in continuous. Okay, so I will, whenever I talk about whenever I consider continuous variables, P will mean the PDF. Okay, because the probability that X lies in the same.
Let's say I have 37, let's say. So I should integrate the probability of X given healthy or sick.
No, but the PDF is well defined, right? The probability density is well defined. Okay, and I'm not asking what's the probability of seeing that particular X value, because you're right, that would be 0. Okay. But because I've already seen it, okay, this thing is fixed here, and the PDF is well defined, okay? So it's everything is.
But you compare the pinpoint value?
Yes.
That depends from the fact, right, that Bayesian rules are equivalent for
that's right.
Continuous and
so Bayes rule, if you take the continuous version of Bayes rule, it's the same, but with the density replacing discrete probability distribution. So I'll ask Roy to do this more carefully, okay? But whoever pointed this out is very correct, and what we'll do throughout the course is just to interchangeably, we'll always use P, but here we'll either use PDF or discrete distribution, okay? For those of you this made no sense to, that's fine, Roy will clarify in this class. But the point is that this, if we do this, assuming this is kosher, what we get is that you should decide that you're sick whenever your temperature is above the midpoint between the health and the sick temperatures. It does make sense, right? It's actually what we do, I think. So we decide that we're sick by more or less when temperature is 38, right? If it's 38, we're pretty content in saying
we're drawing the real prior in that case.
Well, maybe it's 38, considering the prior as well. Sorry? That's right. Oh, no, you're right. It's 38, I mean, the midpoint between those, which is, it's actually lower than 38, right? The midpoint between 36.9 and 39 is, well, I mean, it's just this, for example. And you are right that this, I mean, there are various crimes I made here, except this one, which might be the greatest. The assumption of Gaussianity is clearly incorrect. What's the most convincing argument to why it's incorrect? That we get, well, I guess minuses. It depends on the scale, right? But there is some probability of seeing unbounded fevers in this. Unbounded. Yeah, I mean, the Gaussian is defined for all values. Yeah. That's right. So Gaussian is an incorrect but very reasonable assumption, I would say, in many cases. Okay? But obviously there are versions of truncated Gaussians and what have you.
And could we conclude that depends on the intersection point?
That's what we got. That it's exactly at the intersection.
Even for not equal.
No. For non-uniform priors, it would.
Not equal variance.
Variance? No. Variance will change your results. Okay. This only works for equal. You'll do the non-equal variance.
But the intersection point will not be the.
No, usually not.
Unless the variances work with the priors to bring it back there, but usually no. If whoever wants to go, you can go. Do you have one last question?
Just one question about this rotation.
Yes.
So if you want to know what's the probability, let's say, of x equals 38, assuming that you're on the healthy distribution.
Yes.
So you put in the equation 38, and the value you get eventually will tell you what is the probability that you are higher than 38.
No. Okay. So this is what I wrote here, which is usually written as in this way. Okay. It's a probability density function. Okay. So the Gaussian, if you put 38 in here, it tells you. Well, the PDF in itself doesn't tell you. It doesn't give you distribution. It gives you distribution density. Okay. Probability density. So if you wanted to know what the probability of being between 38 and 38.2, you have to integrate this thing between 38 and 38.2. Okay? But again, we will use PDFs as though they are distributions over X, because as someone said, Bayes' rule applies for PDFs as it does for discrete distributions. Okay? There is a subtle point here, and I'm sure it's clarifying this point.